We're live on YouTube. Hello. Um, welcome. Welcome. And today we are this is gonna be one of the weirdest streams I ever done. But I'm doing my engineering homework and I wanted you guys to come along for the ride and watch what I do when it comes to engineering. Um, and I wanted to show you guys what engineering is kind of about. So we're gonna be doing a stream. So this is gonna be pretty fun. Um, fun. I'm just kidding. This is gonna be very boring. It's like math. It's nothing but like big math, big brain, and math is not fun. Uh, I thought I'd make this really entertaining by doing my homework on stream, and I thought it also would be very convenient to do so. That way, if I needed to come back in the future, um, I would be able to reference my old stream, because apparently YouTube saves what you stream, which is convenient. So yep, this is this is the stream. If I go quiet, it's because I'm thinking. So essentially, what I got here is this is my teacher's video of how to do things, so you might get to hear him. Um, and this is Desmos. Desmos is a fantastic, absolutely free um, calculator, but you could do really cool stuff. So if I want to figure out what this number means, I could just give it a one number, type it in or enter it, or even derive it from something else, and it'll spit me out an answer. If my teacher ever sees this, I'm not cheating, I promise. This is just using my resources smartly. So, sorry, Craig. So let's get started. So what I done was I So the problem here states design a square pin-connected Douglas fir column at an axial compressive load of 90,000 pounds, which by the way that is quite a lot for timber. The unbraced length of a column is 18 feet. So I converted that to inches, got 201 or no, hang on. So what I did was I did something that we normally do that's called a guess. Where I took the force that I have over the max allowable compression strength times the CP, which was a guess, and we got, an area that was required. I chose a 12 by 18 beam, and we're gonna hope that that worked. So I put all my numbers in here, got an answer spit out to me, and we're gonna see if that works. Cause right here is what I did. So let's see. We're gonna take the number we got out, which was 828 roughly. It's like 827.99, which you can see right there. And we're going to put in the area of the beam of 201. We got 116,000 pounds out. We only need 90,000, so this beam is actually, I think this beam is twice as strong as it was necessarily needed to be, so we could choose a smaller beam. Thank goodness, because the beam we chose is 1 foot by 1 1/3 feet. I'm pretty sure. 18 divided by 12. Yeah, it's 1.5 feet wide. That's really big. For timber, you really won't need that much. So what I'm gonna do instead, what I could do is I could just adjust these numbers till I get something right. Um, so let's see. I want So let's go ahead. We'll select a different beam. As you can hear rustling of paper in the background as I flip through pages manically trying to get to the appendix of the book. Here's some timber columns. So it looked like 201 was way in excess. So we're going to jump down to 178, so a 12 by 16 instead. So let's try that. 12 by 16. 12 by 16. Now, if you do the math, 12 times 16, you'll get a different number than 178. Um, when they make timber beams, they aren't actually the size that they are. When you order them, just so you don't have to say, I want a 9.5 by 9.5 beam. Instead of it, they just say, I want a 10 by 10, and you know what size it is, because they're all about ½ inch smaller, which is what I've noticed, but that could be wrong. So we got a 12 by 16 area 178 equals 178. And now we can throw all that back into our calculator. So the D is going to stay the same, but the area we're going to have is going to be a little different. Where do I put an area at? Forgot. K times L. Okay, so the length is going to stay the same. It's not going to change. I'm confused. I got lost instantaneously. Okay, so we have LE over D. D stays exactly the same because that's the same area. Give me a minute. This takes big think to do this. I don't think anyone has commented yet. Nope, I'm the only one watching my stream at this point. Um, so I think we just kind of keep our area till we need it later. I'm pretty sure that's what that's all about. So maybe we could jump down to a 10 by 10 beam, with an area of, I don't know, we'll go 9.5 for D, so 9.5. As you can see, some numbers kind of changed up here. Well, all of them should have changed. Um, but I'm going to do a real cheeky thing where I'm going to just take this last number. Actually, I should. I'm going to add big A equals, what's the area of our new beam? 178? 170. 187. I'm dyslexic. So A equals 178. We'll throw that in there. And we're also going to take a, we're going to make this equal to, what number do we want? What do we want to make this equal to? Well, what is it? It's the F sub something. So then we're going to do F sub. That's the underline button right by, it's the minus key, but you hold shift and then push that the minus key and it gets you a subscript, which is going to be something. F sub something equals F sub something times A. F sub something should be a derived unit by all that. What's this? Oh. Hey. But you let me do other things before. Look. You made me equal F sub C. I don't have any other numbers in there. Oh, come on. 2. Okay, still gonna tell me off. F sub something. Do we have A? Yeah, we got A. How'd I make it do the thing before? F sub something A. A. Okay, so A is working. F sub something isn't. Let's do A. Fa! A. 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 And it's still like, no, that's not something we have. F sub C we have. We get F sub this from here. That should get us that, and that times that should spit out an answer. Um, so that thing's just like, no, we're not going to do that. Okay, well, I guess I have to do it manually. Um, I can do this and just bring this to the top. We could take A times 702. That's a 124,000 pound load we could carry with the beam of that size. So we're getting closer. I'm going to just keep trying beams. Flipping through my book sounds, book noises. Ooh, my voice cracked. Did you hear that? I'm gonna listen back to it. I heard it. That was pretty entertaining. So we're gonna go 8 by 8 instead, or we could or we could take the 9 by 9 and find a beam that's got less area. So I could probably adjust these numbers till I get a number that I like. By the way, so I could probably do this and just get it down to 90,000 and just see which one's closest to 130. There's one for 128. Let's do 128. Ah, so close! Dak Nabbit. Also, my microphone peaked. I'll put it near my throat. Uh, okay. So what size beam we chose? 9.5. So we chose a 10 by 10. So 128 is just a hair too much. We could do an 8 by 8 and then go to like a by 16. But we want to be efficient here. And a beam that is very square is the most efficient. So we want to choose something that's pretty not, or something that is very square. I could go 12 by 12 and 132 and literally just be like, that's good enough. We could do 0.5 again, and we're going to have an area of 132. Okay, that looks 1320. Yeah, that's a big beam. Okay, that's pretty good. So 12 by 12 is probably the most efficient we're gonna get. Let's do 12 by 12 equals an area of 132, which in reality would be 144, but because we have the half inch off, it did math. So, let's see. So we got 92,000 pounds left over with this. So just so my teacher does not have a conniption, we're going to try. I'll write down a 12 by 12 as the final answer. So, yeah, square. It wants a square beam, so 12 by 12 is the answer. The question asks for a square pinned Douglas. Yeah. All right, so let's see. I'm gonna have to explain all this. So we got up here, we're gonna kind of just look at our equations here. So L sub E equals KL. We have K is 1. The beam is supported with a pin on both ends. So that will equal 1. I'll explain that shortly. So the K value, this, if we have a beam that's like a flag post where you got a solid support on the bottom and the top of the beam, the beam can wiggle around. That'll have a different value. I believe it's like 2.1. So just changing that changes what type of beam it is, which is really weird. So 1 times the length, which does not change with the thing, so it's 18 times 12. I'm going to put that in parentheses on my paper. If I had a webcam, I would actually show you guys what I'm doing, but I'm poor and I don't have that. He says having spent thousands of dollars on computer stuff. Philips UA strip and Razer stuff and a headphone stand and yeah, and $100 chair. I got a new chair. It can only really far back. It's super nice. I fell asleep in it yesterday while doing my homework, which is not optimal, but I'm stressed and yeah. I have a class today at 1:30, and right now it is 10:20, 10:11. Hey, it's 10:11. Um, there you go. And because and then it goes all the way to like 8:50. So by the time I leave, drive an hour and 15 minutes to get to school, and then it's like almost 11 o'clock. So like, yep. By the time I get a shower and hit the bed, it's almost 12 o'clock, and then because my class has had all kinds of chaos going on because I live if okay, I'm gonna kind of reveal where I live ish. I live in Ohio, and Ohio's winter this year was pretty nasty. So we missed like 2 weeks of this class in specific, just this class, and yeah, that was not fun. So we got put back 2 weeks, and then our school had a ransomware attack, which was just fantastic. So we also had another week off because of that. So all my classes have decided, hey, let's not cut some of the work away for the students. Let's just squish more of it in the less time. So yeah, we are pretty much double duty now, which kind of sucks, but it's fine. Um, so okay, we got LE over D, E over D. We should have 18.78 alpha equals 0.3 times 1,700,000. That's the modulus of elasticity. I really don't fully understand what modulus elasticity is, but to me, it's how much something can bend, how rigid something is. So we got L E over D squared times 1050. We already have LE over D. So then this spits out 1.37. I'm going to round up because engineers round up everything. So it's going to be 1.377 unit. I don't know. It's just alpha. I don't know what it is. Here we go. The most painful equation to write out because it takes a lot of space. C sub P equals 1 plus alpha. I'm not going to actually write alpha out. 1.6 minus the square root, big square root, of 1 plus alpha over 1.6 squared minus a over 0.8. And that spits us out a lovely 0.7886. We're going to round up that last digit. That's to the 10,000th we stopped rounding at. FC times CP equals 827.998. Again, with the weird number. And then we're going to take this 827.998. We got a little over 100,000. That's quite a good bit over, but it is a square beam, and I'm pretty darn certain that if I chose a beam with any less area, I don't think it would have worked. I'm going to just quickly punch numbers into my super calculator here and try to get an answer out. So we got a 10 by 10, so we're going to do 9.5 for this. 9.5, the area is going to drop way down to 90.3. Okay, yeah, that ain't going to work. That ain't going to fly, Batman. Yeah, and that number there got even smaller, so yep. That's the best square beam we got. So, There you go. See, having a calculator like this to allow you to check what's right and what's wrong really fast is useful. Um, this is not going to be limited to just this assignment. So we got number 24 down on the number 25, which is the exact same thing. So I'm going to need another piece of paper. This class, my teacher's like, oh, I don't like assigning paper tests a long while back when we started the whole thing out. And now he's kind of like, you know what? Paper test. But yet he doesn't realize the amount of paper we spend on just doing the homework is like ridiculous. But it's fine. Craig, if you're watching this, I'm not bashing you. If you ever get this, watch this whole thing, don't bash me. 25. We need a square or rectangle, 2-inch nominal increments, of course. Pin connected southern pine. So southern pine. We change the wood. So write down southern pine. The column length is, how is it braced? Pin connected. It literally says pin connected. So, oh, and then, do we have to do 26 as well? Yes, and 26 says solve problem, the one we're doing right now, if the end conditions are fixed / pinned. So, what? It says it's pin connected. I mean, I could just change the K value. It's no big deal. It does not take very long to do. It just takes a while to write it down. Also, I'm going to go to my live stream here. Oops, that's not my live stream. That's my documents. Can I... Let's see. Oh, look. Aha, look at that. It's an infinite tunnel. So okay. Let's see, settings, streaming. Oh, okay. I was gonna say, I wonder if I could decrease the delay. So we'll minimize that, and we'll continue on. So southern pine, the wood type has changed. We've gone from Douglas fir to southern pine. So some things are going to change. Our F sub C, so this thing's going to change, and E is going to change. I'm pretty sure southern pine's E is like 1.4 million. Do the book. I'm pretty sure that's what it is. I gotta find where the wood is. Where is the wood? D? Is it group C? No. B? Those are pipes. And then wide flanges. So no. See, this is the most time consuming part. Ah, there it is. Southern pine. Okay, E has not changed. Ham fir is the one that's 1.4. But the F sub C has gotten bigger. So it's gonna be, I need that again. It's gonna be 1250 and 1700. So we got another 200 compressive strength. So F sub C is how much pressure the wood can take before failing in compression. I need a drawing tablet. So wood grains are like this, right? In your piece of lumber. So in your piece of lumber, you got like, right? You know, like this is a piece of lumber, and you got the grains of wood going vertically, right? Pretend this is like a bundle of drinking straws. Wood is significantly stronger in the vertical against these straws than it is from this way. So a force from this direction impacts wood a lot more than a force from this direction. So
Yeah, the wood's compression strength this way is way stronger than this way, if you didn't know. So there we go. We can box in this piece of wood. So there we go. So yeah, the wood grain goes this way. So trying to crush the wood from this direction, it's much weaker than this way because it's like pushing on a bundle of straws. If you get a big bundle of straws, and then tie them together with a rubber band and try to push down on them from the top, they're actually way stronger than if you try to squish them from the side. So, and wood is like that. Steel is not like that, so we don't have to worry about SFC. It's the same for all metals. But those are usually given to us beforehand. So yeah, this wood is stronger down the grain or parallel with the grain, which is great. All right, let's see. So our weight we need to try to support is 48,000 pounds. I'm running F sub C is 1250. E is 7,700,000. About says 17 million. It is not. That'd be a very strong beam. We're gonna go right 25A right here. So we're gonna have 48,000 pounds, which is going to be an arbitrary number. We're gonna have to fiddle fart around with that for right now. So I have a large equation down here at the bottom. We could just type in 48. That's 28. 48. 4,800. 48,000. This number here gets changed. We're gonna keep this number so it's a good guesstimate, and we got 90 spit out. So we need a beam with an area of at least 90 inches. So I think a 10 by 10 is really close to 90. So we're going to do 1,000, writing on my piece of paper, 1250 times 0.85. My throat's starting to hurt. I need to get water. So that's that. And that equals 90.35 gas. I'm gonna write gas beside it because that's what it is. I'm gonna be right back. I'm gonna go get something to drink. I'm very thirsty, so the stream is just gonna kind of go dead, but I'll run, so don't worry. I'll be right back. I'm back. So, all right, let's continue the homework. Let's continue the math. I have brought Gatorade and water. Oh, I can hear myself. I kind of don't want to be hearing myself. Um, so okay, let's see. So we're gonna do um, what am I gonna do? Right. I got to get back on track. So the area we need is 90. So let's find a beam with an area close to 90. It could be rectangular, so we're probably going to go just a hair above 90. So we're probably going to choose like a 10 by 12. So we will have a little bit of extra headroom. Um, so yeah, wow. Okay. You know what? We're gonna go with it. We're gonna go with a 10 by 10 because its area in the book is 90.3. It is 5 hundredths underneath, so we're gonna go with that. 10 by 10 equals area equals 93. Um, so we're gonna do that. We'll see how that goes. Um, so let's get started. So we're gonna go ahead, put in our area here of 90.3. Some of those numbers changed, but our length is 16 feet. So 16, so our length is going to go shorter, so our beam will be stronger. Kind of think of it like a ruler, right? It's really hard to bend a short ruler, but it's really easy to bend a big ruler. Like that analogy is pretty horrible, but I mean, I guess it makes sense. The K value, I'm going to leave alone. I'm not even sure. I mean, I could do this and just make math happen. So, yeah, a lot of math is happening right there. Oh, I stopped it on -1. I mean, I need +1. So, there we go. D, we're going to keep the same because it's the same. It hasn't changed. And now let's go ahead. We're going to change. No, we're not going to change anything. I'm going to go ahead, put in 863 here. 863. And 77,000 pounds is the amount of load we can carry. I think we could go with a smaller beam. I'm going to try to be like super efficient and grind this one out to get like the perfect beam. Because this is fun. I have a nice, easy, stress-free way to do this. So we're going to go with a, well, let's send it 6 by 6. So we're going to go 5.5 on this. 5.5. The area we're going to go with is 30. 30.3. So 25,000. Okay. 6 by 6 is very small, but we can probably get one that's got an area that's sufficient. So 52. 52. Ooh. 44,000. Let's go a little bit bigger. 63 is the next biggest one. That's 54,000. That's a little overkill. Maybe we can go an 8 by 8. So 7.5. 7.5 with an area of 56. We'll go with the square beam. Okay, wow, that's really close. Max load we're supposed to have is 48,000. That they're saying we're gonna get like 40,000, like 48,000. I really need to get a 642. 642. It's 35,000. Okay, never mind. I really need to get this. Okay, I'm gonna actually copy this equation. I'm going to paste it down here, and I'm gonna add the area to it. So A. There we go. Now we're gonna get a live readout of what we're gonna get out of this. So now we can adjust all three factors at the exact same time and get a live readout of what we're supposed to have. Because area is supposed to be times this number, so as you can see, they're really stinking close to each other. They're by 10 off. So, and rounding up, they're gonna still round up together. So they're close enough. Because this has got the decimals and everything mixed into it, so it's more accurate anyways. This is kind of a guesstimate. So we'll get rid of you because we don't need you. Goodbye. Let's see. So we're gonna need well, let's keep going through areas then, I guess. That's really all we have to do is just keep choosing an area on a 8 by 8 beam. So 71. How's 71 look? 45,000. We're getting closer. 86.3. 55,000. A little overkill. Let's go with a 5.5.
5.5, and we're gonna go with a 85 beam right there. 32,000. How about 96? 36. How about 108? Nope, we don't have a 6x6 beam large enough, so we're gonna have to go with 7.5. Just crank the number all the way up, yeah. So 71. I just heard that back. 86.3. Okay, 86.3 is a bit overkill. Let's go with the 9.5. So 10 by something. 9.5, and we could probably go for like oh. So these beams are like a whole order of magnitude stronger. Um, let's just max this out and max that out. There we go, and we'll min this out. So we'll be like 4 and like half an inch. Okay, so there, this thing works to like any size beam. I'd like to put that on a thing. Anyways, so 7.5 is kind of the sweet spot, I guess. Um, Jeez. It's a very, very long beam, but very, very small. It's like an 8 by 1/4 inch or something silly like that. 71. 71 is pretty decent. It's close, but 86 is the money. I think it's the closest that's actually over the strength we need. So yeah, this is really easy. You just throw numbers at it and math comes out. Um, so this saves me a lot of time doing the problems. And if this is accurate and this is correct, this is the fastest way to do this homework. And it's also entertaining because you can just kind of pick numbers and go silly. So it's great. Stay hydrated, kids. So let's see. So for a load of 48,000 pounds, the type of square or rectangular beam we're going to need is going to be a. Oops, I didn't look. I didn't take note of what beam it was. It's going to be a 8 by 8 by 12. So an 8 by 12 beam. 8 by 12. Thank goodness none of these are in metric, because this whole equation system would slightly break. Because I'd have to do a lot more converting. This, I could just spit numbers in and I get answers out, which is useful. But thankfully the last problem is different. So 25A, 25B, 8 by 12. We're going to put down the amount of force it can actually carry as well. 55, 20, 44. 55,244. 55,000. Wow. What I said there was absolutely horrid. So let's see. So we already solved that problem with literally just 3 lines written on the paper. We could literally go paperless. We could totally just put numbers in here and just get answers, which is amazing. But I think handwriting down the problems is going to be useful, because when I turn in the homework here on Blackboard, yeah, my mouse is finally moving again. When I turn in my homework here, when I turn in the homework over here, I'm brain farting here. Sorry, I'm hearing my own voice over my phone, and it's really messing with me. Yeah, when I turn this in over here, it's going to request me to put in all the parts of all the problems. So like, what's the alpha value for this problem, and then what's the f sub c, what's the c sub p, and what's the required area, and it's going to ask me what's the area, what's the f sub c of this wood, and what's the length. It's going to ask me all that stuff. So just kind of having all that there and done, written on the paper, makes turning it in so much faster.
If he changes how the problems are like done as well, it's no big deal. I'm not really worried about it. So let's see. Let's start with the K times L is 1 times 192. LE over D is 25.6. Alpha equals 0.3 times 1.7 mil. He'll know what I mean. Divided by 25.6 squared times 1250. And that's going to get us out 0.6226. I'm going to be really accurate with that. F sub P, or F, that's totally an F. That curvy letter, the one that's shaped like a C, that's totally an F. 1 plus alpha over 1.6 minus square root of 1 plus alpha over 1.6 again, square that minus alpha on its own over 0.8, and that gives us 0.5139, and the next two digits after that are zeros. So we're going to do FC times CP equals 642.3 or 4, because rounding up, and then total force total equals 55,244, because I can read numbers. And yeah, and that spits us out a final answer. And now all we have to do is just change the force for part B of this problem. So where do I have an input for a force? No, I don't. I have an output for a force. He's probably going to be like, wow, this kid's really good at guessing, or he's really good at looking up the answers in the back of the book. So we need 60,000 pounds of load to carry. So I think we can probably step up to the 10 by 10s. So we'll go 9.5, and we're going to step the area up to 90. And that is, how close are we? Because I feel like that's really close. Yeah, it's only 8,000 off. Actually, that's pretty stinking close. I want to see if we could get a little closer, though. I want to see if we could get a little bit closer. So let's see. We need 60,000. So let's go with 8 by 14. So 8 by 14 is going to have an area of 101. And it's going to have a D of... Wait a minute. I put my D in wrong. Oh god, that's a horrible thing. I should never have said that. Oh no. Thankfully, it's just me watching this stream, but if anyone goes through the whole thing, they're going to get a treat. Well, my stream's going to get canceled now. Okay, yeah, that's way too large of a number. So I'm going to do something. 161. Let's just like 161. Okay, we can get to the numbers that are big enough to do that. 8 by 12, so 86. 55,000. 101. Getting closer. 116. And we're way into the 70,000s. So yeah. Let's do 9.5 with a square beam. So 90.3. 76,000. It's way overkill. Let's do a 6 by 16. So 5.5. And we're going to shoot this way up to like... Well, what number would we need? We need 178 area. Nothing has that size. So we got to go up to 7.5. And let's put in the number and we'll see which one's the closest. So we need 60,000 exactly. 93 is the closest. 86 and 101. 101 is 4,000 over. Now, one problem I kind of don't like with the homework that I hope Craig shows a little mercy with is the fact that we could choose any beam we like, but there's only certain ones that he may count right. And I kind of don't like that because that leaves me like, if someone chose this, like if someone chose a certain type of beam, like, and it's a good bit over, but it's not the closest one, like, will he still count and be like, yeah, I mean, they over engineered it, but like, they was pretty close. Because there's like, because you saw all the answers, like, this one here seems to be the closest. But imagine handwriting. Every time we changed our mind or changed our beam, imagine hand writing it out. Like, that would take way too much time. That would take way too much time to properly do.